So let's suppose that Q1 and Q2 are in these two locations, and that both Q1 and Q2 are positive, or that they're both negative. Okay, in other words, they have like signs. So what I want you to do, based on general knowledge that I would hope you'd have by this point, but maybe not, and if not, we'll easily correct that in a minute. I want you to draw a vector, about this long, that represents the vector F12, the force exerted by charge 1 on charge 2. So sketch that vector. You should pause because I'm going to go right into it. Okay, you should have sketched your own vector. But the vector will be, if it's about as long as I said, it's about right there. So there's your vector F12, pushing Q1 away from Q2, away from Q1. This is because, as you should know, but if you don't, here it is, like charges repel, unlike charges attract. And when they repel along the line connecting the two charges, which is why I had that dotted line there in the first place. So this vector would go right along that dotted line. Okay, now we don't know how big or small that vector is because we don't know what scale we're using for the magnitude of the vector. 1 centimeter could equal 10 billion newtons per Coulomb, and of course that's the unit for a charge, as we'll see very shortly, or for a force. Think an electric field. So ignore what I just said, but it could be several billion newtons, or it could be just a couple of micronewtons. We don't know because we don't know what the scale is. In any case, okay. What is the charge? What do you think is the charge? F21. And can you sketch that? Pause for a second. Sketch that. You should have a sketch of this. But here it is. It's going to be like so. So it's going to have the same magnitude as this vector. Don't know if I really achieved that with my sketch or not. And it's going to be in exactly the opposite direction because these forces have to act along the line through the two charges. Okay? Now, can you sketch if the charges are unlike, if one is positive and the other is negative? Okay, hopefully you've done that. I've drawn the charges. You could have drawn them anywhere, as long as they're not right together. But if they're unlike, one positive, one negative, then the force will be one of attraction. And I'll draw the vectors about as long as I did the last time, but the two vectors will be like this, where this is F12, the force exerted by charge 1 on charge 2, and this is F21, the force exerted by charge 2 on charge 1. So we've applied the fact that like charges repel and unlike charges attract. Like charges here, unlike charges here. Now, what I want you to do is I want you to calculate K Q1 Q2 over R squared if Q1 is 3 microcoulombs and Q2 is 5 microcoulombs, and R is, I said 0.2 meters, okay, if R is 0.2 meters. So go ahead and do that calculation. So you don't have to go back hunting for it. Let me just reveal the value of K again. Here's your value of K. Okay, the calculation is really straightforward. K is 9 times 10 to the 9th Newton meter squared per Coulomb squared. Q1 is 3 microcoulombs, which is 3 times 10 to the negative 6 coulombs. Certainly know what micro means. If not, take a lesson. Should have known that a long time ago. Q2, 5 microcoulombs, 5 times 10 to the negative 6 coulombs. And you're dividing that by the square of R, and R is 0.2 meters. Okay, so that's quite easy to calculate. You calculate that in your head. I can calculate it in my head. Hopefully some of you can calculate it in your head. 10 to the negative 6 times 10 to the negative 6 is 10 to the negative 12th. 10 to the negative 12th times 10 to the 9th is 10 to the negative 3rd. 3 times 5 is 15, and 15 times 9 is not 27. I just multiplied the 3 by the 9. 15 times 9 is going to be 135. Okay, so we have 135 times 10 to the negative 3rd newtons, and then that's divided by the square of 0.2 meters. Square of 0.2 is 0.04. The square of a meter is a meter squared. We notice in the numerator the Coulomb squared here in a denominator is divided into the Coulomb times the Coulomb, which is a Coulomb squared in the numerator, so the Coulomb unit goes away. And we see that the meter squared unit is going to go away, leaving us newtons, which is just exactly what we want now. Dividing by 0.04 is the same as multiplying by 25. 4 pennies, 4 cents goes into $1.25 times, whatever you want. And 25 times 135 is what? Well, 25 times 100 is 2,500. 25 times 30 is 750. And 25 times 5 is 125. And I believe that gets you up to 2,500 and yeah, 30 gives you 750, that's 3250, and then 125 is 3325. Okay, 3,325 times 10 to the negative 3rd newtons, which equals then 3.325 newtons. Check my arithmetic. I'm not as reliable as I used to be, and I never was all that reliable. Now, maybe you've checked by now. That should be 75 here, because we're adding 125 to 3250, so that's going to give us 75. And I discovered that if I just did a long division of 4 into 135, 4 goes into 120 30 times, that leaves you 15. 4 goes into 15 3 times, with 3 left over. 4 goes into 3.75 times, there's your 75. Okay, well, I still advocate knowing how to do simple calculations in your head. Now, I'm going to pose one question, then we'll go on to the next video. The question I want to pose is, what will be the vector force in this situation if these coordinates are in meters? Okay. And same over here. I'm not going to label it over here. And we have a force of 0.004 coulombs here, and that's kind of a large force, a large charge to be holding at a point. It's kind of difficult to even build that kind of charge on a small object. And negative 0.002 coulombs here. You might be wondering what a coulomb is. Right now, let's just get the mathematics done, and then we'll illuminate that a little more very shortly. So what would be the force between these? Let's say the force of this charge on this charge. So let's call this Q1, and let's call this Q2. And we want to find the vector force F12. That is the force that this charge exerts on this charge. So you might go ahead and do that calculation. That's what we're going to do in the next video.